Welcome to Statistics. We're going to be looking at sample distributions today and a couple of the ins and odds of things, as well as a couple of examples to go along with this. So, here we go. So, when we talk about sampling distributions, one of the ideas that we need to remember is the difference between statistics and parameters. I have some information there for you, but the basic idea here is that a statistic is a found value versus a parameter is a wanted quantity. Okay, so one of the big pieces of this is the mean. We have mu and we have x bar. X bar would be your statistic, whereas mu would be your parameter. Same is true with your standard deviation versus your value for sigma. So the idea here is that we don't necessarily have the ability to find the exact value of the parameters, but we can find statistics. Like, for instance, we know that the mean annual household income for 60,000 households is $55,600. And that is the current U.S. statistic right now in 2023. That was actually published in February this year. The mean, the value for u here, or mu rather, is unknown, but we do know the x bar value, that we can find that based upon some statistics, the values that we've actually collected, the data that we have on hand. So that statistic is going to be what we're going to use for our parameter. Okay, so the idea behind parameters is the value for the populations. So the population standard deviation and the population mean, those are different. Those are the parameters versus the statistics, which the statistical mean, or the sample mean, is x bar, which is an estimate for the parameter of mu. The sample deviation, which we'll call s, is an estimator of the lowercase sigma there. So the statistics are the estimators of our parameters, and in many cases, the best we can do is that estimator. Okay. Now, a couple other odds and ends about this is that we can't actually, maybe in some instances we can, but most of the time it is actually impossible for us to find the exact value of the parameter that we're seeking. So the best we can do is seek the approximation of that. It's the best sample. Now, the idea behind the best sample is what is the best quantity we can pull in here. Okay, so one of the ways we're going to work with that is to work with this idea of very large quantities, very large numbers. So as the number of observations increase, that x bar value gets better and better as an approximation for our own known value of mu. Now, in some instances, we are actually going to assume that mu is a particular value, and that x bar approaches that value as we get larger and larger. Now, one of the things it also tells us is it can tell us whether our value for mu was wrong or right. So some of you are asking, well, how do we know what that value is? The answer is we really don't necessarily know that, but we have to start somewhere. And that's one of the aspects of statistics, is that we are collecting data, we're collecting to try to understand it better. And it starts with us digging in and trying to understand and identify how well do we actually know this information? What can we really say? And we're going to look at how confident we can be in those values that we get. Now, observations need to be random from our population, right? So that's a couple big things. When we say that word best there, we're talking about the sample's large, and we're putting that large word, or at least I should put that large word in quotes, and the observations that we're collecting are random from the population, as opposed to we're strategically picking them. And that's going to help us to make this a good estimator. Now, the population distribution, so the variability of the distribution is of the population. Again, that's some of those things that we have an idea of what that population might look like, or things like that, but that's still based upon a sample. So the best we can really do most of the time is to use the sample distribution to build the population distribution. Remember, the population is the entire group, and most of the time it's just too expensive from a time perspective, in a data perspective, to actually be able to collect every single piece of data. And the fact is that we don't actually need to, based upon a good sample distribution. Okay, so the better that sample distribution is, the more it's going to properly reflect our population, and any assumptions that we've made about our population that might be wrong will work their way out as we collect our data and we refine that process with our data. Now, one of the things is that we want to look at when we collect our data in looking at our sampling, not our population, but our sampling data, is it normal? One of the assumptions that we're going to make most often is we're going to assume that the data is normal. And once we know that, or we can verify it is, or that it looks like it is, we can move forward with that. But even with it not actually being legitimately normal, we can go ahead and make that assumption, because then we can actually start answering questions and asking more questions as well. Also, the center of the distribution is close to the mean is another thing that we're going to be looking for. And again, the variability is the standard deviation sample close to the population standard deviation. So we want to look at all three of those pieces. Is it a normal? Is the center of the center of the sample close to the center of the population, meaning are those means close to each other? And is the variability close to each other? Again, you would say, well, how do we know what it is for the population? Well, we would make these assumptions again, and then we're saying, are our samples close to what we expected to get? And there's a key aspect of that. So one of the ways we're going to go after this is we're going to deal with the sample distribution of X bar, right? And we're going to base our calculations upon the collected data that's going to give us this value for X bar. All right. Now, as we go through this, one of the things that we want to work on is what can we do? What else are the other things we can do with this? And we come across this idea of, well, we can build our sampling distribution of X as using mu. And again, what we're doing here is we're saying that X bar we're going to use that as our mu value. And then our standard deviation is going to be a given quantity divided by the square root of n. So we would have found our standard deviation, and then we're going to do the square root of n business. And that's what this does for us. Is it gives the focus of this is basing X bar as an unbiased estimator of mu. And that's again based upon the sampling being random and the value being the number of values that we're using being large enough. Okay, so what do we do now? This is I'm going to work an example here in a second. One of the things to remember is that our standard deviation, when we do this process, I mean, just think about this. We're taking this and we're dividing by the square root of n, which means we're going to end up with a smaller variation. This increases the precision while also increasing the expense, okay? So, and what I mean by that, in statistics, a lot of times what we're talking about when we talk about expenses is not necessarily money-wise, although that can be a factor. We're talking about time and collection and the data itself. The larger n gets, the more values of n that we need. So if we have n equal to 10, well, that's not very many pieces of data that we have to collect at all. If we're talking about n equal to 1 million, well, that's an extremely expensive data collection. How do you get 1 million pieces of data collected? And that becomes an expensive process. Another piece of this is that n shouldn't really need to exceed 5% of the population, because after that, we really don't get the variability that is needed anyway. So let's work through an example here. So what we're talking about here is total cholesterol levels of men aged 30 to 34, okay? And then we have this mu value here of 182. And of course, we're saying this would be the original X bar value, and our standard deviation of 37. Again, so these would have been kind of found quantities of previous ideas. So now we're looking at 100 men. And we want to know, well, the first thing we want to do is, what is the distribution here? What's the sample distribution? And just to kind of answer that question, well, we know that's going to be n, and then what is this? Because I'm saying, well, how do we know it's n? Well, we're making the assumption that this is going to be a normal distribution, right? So if it's a normal distribution, then we just need to identify those pieces, right? So we're doing 100 men, and mu is going to be our X bar value. Okay, so this is 182 here. So that piece is taken. But what is remember, this is always mu and our standard deviation. So it's our mean and our standard deviation. What is this standard deviation that we're going to use here? Is it 37? No. What we need to do, okay, is we need to do this approximation that we're just talking about, where standard deviation was equal to this other value over the square root of n, right? So we're going to do 3.7 divided by 1, the square root of 100, which gives us 37, which gives us 37 as our standard deviation for this. You see how much that reduced that. Now what that does, when you think about the variance here, is we've reduced the amount of variation in our data set, which makes it more accurate based upon these values here. So the square root of 10, or square root of 100 is 10, 37 divided by 10 gives us 3.7, so we've increased our accuracy. So there's our sample distribution. Now the next question we have, and I have this written out, is what is the probability that a random person picked from our 100 men here has a cholesterol level, total cholesterol level between 180 and 184. Okay, now there are lots of ways we can do this. You can pick out statistical softwares, and they can actually run these models for us fairly quickly and easily. But the other thing we can also do is we can run this as a standard normal process here. So if you remember, what we'd want to do for that is we take the random variable minus our mean and then divide by our standard deviation, right? And we do that across the bar. So we'd have x bar, right, minus our mean divided by our standard deviation, and then do the last one. So 184 minus 182 divided by 3.7, and we get that. Now this means that we have P is whatever this quantity is. I don't have that exact quantity in my head. I think it is, yeah, here it is, 1.71, negative 1.71. That's less than or equal to Z, and that's less than or equal to 1.71. The other direction, now, you think about, some of you may be thinking, well, those numbers are oddly symmetrical there. Well, yeah, of course they are. Remember, when we do a Z standard, what we're doing is we're recentering our mu value to 0, right? And this x bar was 182, so this 182 minus 182, so there's putting it to 0, right? And then dividing any 0 by anything, so it gives us 0. So we're recentering this around 0. And 182, 2 to the left, 2 smaller was 180, and 2 larger is 184. So this is, by its sheer nature of what we created here, symmetrical, right? So we're saying, not quite one standard deviation above, almost, I guess, half a standard deviation above and half a standard deviation below our mean is what we're talking about. Not quite, but pretty close. So we've redone this as a standard normal. Now, why would we do that? Why would that be interesting to us? Well, because now we can look at the Z table and we can get our Z values out of there. And what we do with that, when we find that, is that we find that the upper bound here of 171 is 0.9564, right? And then we're going to subtract off the lower bound, which in this instance ends up being 0.0436, giving us a total of 0.9128. Now, a couple of things. Let me back up here just for a second, okay? So first thing is I want to point out that we are talking about this standard normal curve. So we go to our table. All right, and please pause this, rewind this, and watch this a few times. So we go back to our standard normal table, all right, and we find 1.71 on our table, okay, and we find that value, and that would be this lower bound here. Now you may be thinking these are smaller. I'm reversing the process. So I'm saying that if I color code this real quick, this value right here corresponds with that one. So those two yellows go together, and then I'll use the light blue here. Those two right there correspond and go together as well. And the reason why I'm matching those up that way is because this is the upper bound. The blue one here, the 1.71 is the upper bound. So more of the data is going to be below that quantity. And then negative 1.71, well, very little of the data is going to be below that one. So we need to subtract this off because remember, this is a cumulative table starting at the left and working our way to the right. So we're going to start at the right-hand side because that's going to be our larger one, and subtract off the smaller one to get what's in between them. So now, what is this quantity over here that we just found? This is the percentage, if you will. The original question actually here was, what's the probability, I guess is another way to word this, what's the probability that we pick somebody and their blood cholesterol level, total blood cholesterol level is between 180 and 184? And this is what we come up with is 0.9128. So it's highly likely that we would pick someone and end up in that realm right there, which is interesting and useful. There are lots of different ways you can use this. Another way to look at this is to say whether someone is plus or minus 2, and this works out to be milligrams per deciliter of cholesterol above or below the mean of 182. And what this means is that it's a 91%. So most of the population, according to this, lies in that realm. 90+% of the population would lie in that realm between 180 and 184. Such a huge chunk. So anything outside of that would be a very small portion. You're talking about a very small group of people there at that point. And then you could redo this entire process again for, say, 1,000, right? So if we go through and we recalculate all this for 1,000, what does that do? Well, the first thing we have to do is redo our standard deviation, right? So that would be, in this instance, 37 divided by the square root of 1,000, if we're let n equal 1,000 this time. And all I'm going to do here is we just do that calculation, and when we do that, we end up with, I gave you the wrong values a second ago. These are, I was looking at my notes wrong. So let me redo this. So this upper value here, this was negative 0.54, and this value is 0.54, which means that we're doing 0.7054 minus 0.2946. So some of you have been following along and pausing as you go, and you're like, how did you get those values? Well, I didn't. I just wrote my notes wrong. I apologize. Now, that means that we do that subtraction, and we end up with 0.4108 of the population. So the probability that someone has between 180 and 184, okay, and this is based upon this sample being 100, all right? So of those 100 people, this is 4108, right? Now, if we repeat this process for 1,000, that's when we get this other quantity that I was referring to a second ago, okay? And in this instance, we end up with 1.17. So now my distribution is 182 and 1.17. Now that is a much smaller standard deviation, so when we do plus or minus, the 2 units off of our mean, we're going to have we're talking about it being almost 2 standard deviations outside of that realm, which actually makes more sense, right? Because before we were talking about it being less than a standard deviation, about half a standard deviation outside. So we're talking about 0.4, or roughly 41% of the population. Here we're talking about it now being a much larger. We're talking about 2 standard deviations, and that value, if you remember correctly, that ended up being P was negative 1.71, so less than or equal to Z, which is less than or equal to 1.71 by the process we would have done up there earlier. We simply subtract off 182 and divide by 1.7. Same thing here is subtract 182 and divide by 1.17. Gives us those values, and when we do the subtraction between our higher and our lower bound, we end up with that 0.9128 like we did earlier. So this means that 91% of the population is in there. So what is this and how is this useful to us? Well, what we're finding there is if we increase the population size to 1,000 here, we pick 1,000 people, we're more likely to be including people with this realm of values here, as opposed to a smaller group. All right. So what this tells us is the difference between these two things. If you're looking at this, the larger the group, right? I guess if that makes sense, right? Spend a little bit of time on focusing on what that means. But if we're choosing 1,000 men from this population, the probability that value of X bar, right? Okay, and this is what we're referring to. The probability that this X bar value is going to reflect the population that we chose is now 91%, versus earlier when we only chose 100, the probability that this X bar value that we have of 182 reflects the population is 41% of the population, or 0.4. So that's the difference in those probabilities, and what they mean is it changes. The larger the group of the population, the more accurate we're getting. So what we're saying is that this value is, this 182 is probably mostly in line. If we keep going, get bigger populations, it should continue to fit in quite well. Okay, I hope that makes sense at least. All right, so we got a couple more slides here I want to run through with you. Central limiting theorem. All right, when n is large, the idea is that it gives us the ability to kind of refocus or recentralize our data on things that are a little bit more useful to us. It allows us to be able to build a more normal probability distribution, which allows us to be able to do normal probability calculations, which is extremely useful, as you just saw with being able to do z-scores with that. This is all based upon a couple of pieces. One of this is that you still are dealing with a truly random sample, or a random sample as much as you can make it random. It provides less variability, and it is significantly more normal. It's less variability and more normal than individual observations. So what that means is if we take an individual, it doesn't mean that individual is definitely going to fall within that realm of 180 to 184. We could pick 4 or 5 individuals and all of them could fall outside that realm. But as we start to pick more and more and more, and we do more and more observations, what we should see is the variability decrease and the look to start to look more and more normal. It's kind of the idea if we roll 2 dice and we just do 5 rolls, well, we're not going to get a whole lot there. There's a possibility that we could get 5 different rolls and it could look uniform. But if we do a couple thousand rolls of the dice, we should start to see something that looks more and more normal, and the variability between the means, as we continue to recalculate that as we go, is going to stabilize. And that's one of the things we're talking about with this piece here. Okay, so I have another example to run through here. And let's just say that we're talking once again about this idea of what can we do with the information here. Okay, so we're going to look at the time a technician is required to perform a preventative maintenance on air conditioning unit. It's covered by an exponential distribution, and it arises, this is not something that is centralized to any one profession or anything, but it is something that is looked at, and these algorithms do actually run actual decisions, okay? So many engineers and industrial problems, such as failure of a machine, is based upon these calculations. What's the probability it's going to fail? When should we do preventative maintenance to ensure that we don't have to do major overhauls that cost us time and money? We can plan maintenance that is a lot more useful to us than unplanned repairs. So what we're going to do here is we're going to take the mean time of an average, that should be X bar there, of 1 hour and the standard deviation of 1 hour, which means that the time we're taking here to run preventative maintenance may take no time at all. May go out there and discover, nothing's wrong, no maintenance needs to be done. The average is going to be an hour and the standard deviation is 1 hour, so maybe it takes one standard deviation so that puts us between 0 and 2 as being one standard deviation in either direction. He has a contract to maintain 70 units in an apartment building. You must schedule the technician time for the visit to this building. Is it safe to budget an average of 1.1 hours for each unit? So how do we go about doing this? Well, the first thing we want to do is go ahead and start building the normal process for this thing. So let's keep those values there we got in mind, and actually have this kind of set up for us down here. Is once again we have our mu value of 1. That's our x bar value that we're going to assume to be the unbiased value, okay, or unbiased piece there. And then we're going to take our standard deviation. So we're going to do 1. Oh, let me get my. We're going to do 1 divided by the square root of 70. Okay, and when we do that, we end up with that being 0.12 hours, mind you. Okay, so when we do this normal approximation here, we're talking about this being 1 and 0.12. So the distribution here, now what can we do with this? Well, what we're going to do with this is we're going to say, and again, you can use some programmings here to figure this out. So we're saying, what's the probability that any given repair or maintenance schedule incident is going to take more than 1.1 hours? Okay, so the question was, is it safe to schedule everybody for 1.1 hours? Is that a reasonable value? Because we're going to be looking at this probability here, and as that probability is too high, too low, then yeah, okay, we're good to go. But if it's not, it doesn't fit in well, then we probably don't want to do that. There are programs out there that will figure this out for you based on normal, but we also have our z-table. So I'm just going to go ahead and switch this over to a z-standard. So I'm going to do the probability of x bar minus 1 over 0.1, and that's going to be greater than 1.1 minus 1 over 0.12, okay? Which means that we're looking at z being greater than 0.83. So if we're wanting z to be greater, remember our z-tables figure up for z values being less than, right? So we'd have to switch this. So it's going to be going the other direction. So 1 minus whatever this value is. So when you look at your z-table, you're going to find 0.8 on there, and you're going to go over to 0.3 in the other column, and you're going to find what value matches up, and you're going to find that matches up with 7,967, which gives us a grand total of 0.2033. So let's interpret this. What does this mean? What this means is that when you're talking about scheduling 1.1 hours, what's the likelihood that your any given maintenance work is going to take more than 1.1 hours? And you're saying the probability of that occurring is 20%. So 20% of the time, it's going to take more, or there's a likelihood that of 0.2 or 1/5 that the maintenance work is going to take more than 1.1 hours. So is there a chance that you're going to need more time? Yes, there's a 20% chance that they are going to need more time than that. Meaning that the repair work needed is not going to be done in the time allowed. If we redo this process and we say, well, what's the probability of x bar being greater than 1.25 hours? Well, just redo the calculation just like we did above that, right? You go through the same process, subtract 1, divide by 0.7, right? And then when you do that, you end up with the value dropping down to about 0.02. So if you budget 1.25 hours, you see a far smaller likelihood that it's going to take more time. Therefore, do you schedule for knowing that the 20% of the time is going to take more than the time allowed, or do you schedule for when you know it's going to take 2% of the time it's going to take more than the time allowed? The idea here was probably that it'd be better to schedule for the lower one because you have a schedule to keep. You talk about financially, this might be impacting service quantities, or your customers maybe get annoyed because you're like every 20% of the time. So if you have 5 calls that day, one of those calls is going to take significantly more time than the others. So if it's the first one in the day and it takes more than the hour allotted, that's going to move the entire day back and cause problems for the rest of the day, theoretically, or based on these probability models. But if you schedule 1.25 hours, there's the chance that it's going to take less time and the day could actually end sooner than normal. And your technicians and your customers will probably prefer that. So going with that 1.25 would probably be the better way to go because that contains more of the quantities that we're actually interested in. Okay, meaning that 98% of your jobs are going to be done in 1.25 hours, which is a good thing. Okay, so I hope this information is useful. I hope these examples helped add to your understanding of what we're talking about with these normal distributions and how you can use these sample distributions to make decisions. Please rewatch and rewind and let me know if this is useful to you. All right, take care.